So it is a great pleasure and honor for me to give the Oberwolfach-Vorlesung this year, and I thank Martin Greuel very much for the invitation. Well, characteristic classes I met for the first time when I visited Heinz Hopf in Zurich in 1948 after 3 weeks of work on a Swiss farm. And I also like to mention, of course, that Heinz Hopf already visited Oberwolfach after the war in 1946. Well, when I visited him, he explained the Poincaré-Hopf theorem to me, which he had announced at the meeting of the German Mathematical Society in Danzig, 1925. So, let X be a compact differentiable manifold, let's say of dimension n, and V a vector field on X, and we assume that this vector field is defined and continuous outside finitely many points, and that it is also different from zero outside these points. These points are called singularities. And then the Poincaré-Hopf theorem says that the number of singularities is always the same, independent of the vector field, and namely it is the Euler-Poincaré characteristic of X, the topological invariant of X. Of course, one has to count the singularities with the proper multiplicity. The standard example is the two-sphere, where you march always towards the north and have such a vector field. Then it has two singularities of multiplicity 1 at north and south pole. And the Euler number of X is 2. Yeah. Now, we, after this theorem, we immediately go over to Chern classes. Yeah, which I also met with Heinz Hopf just a little bit. They were not very known yet, but Chern had written the first paper, 1946, in Annals of Mathematics. And later I learned something about them in the book by Steenrod on the topology of fiber bundles, 1951. And now I try to give you the definition of the Chern classes. So suppose now we have a complex manifold. Of complex dimension n. So this will be a differentiable manifold of dimension 2n. And then, the Chern classes come up as follows. We try to construct an R field on X. This is an R tuple of vector fields on X, which we hope at every point are complex linearly independent. This will not be possible, but it will work outside a 2R minus 2 dimensional cycle, which represents a certain homology class. Yeah, so this is you can imagine this as a 2R minus 2 dimensional subset. And this homology class lies therefore in the 2R minus second homology group of X with integral coefficients. And for R, and this homology class which we obtain this way. So this is a cycle of singularities. On this cycle are the singularities. And then for r equal 1, when we have only one field, one vector field, then of course complex linear independence, just that this vector field is different from 0, should be defined. And for r equal 1, we have a fixed zero-dimensional homology class, and this just means that we have a number, the Euler number. So this then, Chern studies cohomology classes. The homology theory in dimension 2r minus 2 is by Poincaré isomorphism. It corresponds to the cohomology in dimension 2n minus 2r plus 2. Yeah, we go over to the dual dimension and of x. And then the element we get in this way by passing from the cycle of singularities to the cohomology class. Yeah, this is the cohomology class C and R plus 1, the Chern class with index n minus R plus 1. Yeah, I hope I did not make a mistake. For r equal 1, we have a cohomology class of complex dimension n, so of dimension 2n, which by the duality corresponds to a zero-dimensional homology class. So this thing here belongs to the manifold and is lying in the cohomology class, in the cohomology group here, which I wrote down already, so of X. And these are the Chern classes. So we have Chern classes C1, C2, up to Cn, Ci in H2i of the manifold. Yeah. Now, if we have this, we can introduce Chern numbers. Yeah. We should say first by find out that this takes place in the cohomology ring of X. The cohomology ring of even-dimensional cohomology classes, which is commutative. So we have no problem with the dimension, with the ordering them. So I can take any combination of Chern classes, let's say R of them, such that the sum of the indices is n. Then this is a cohomology class of dimension 2n, so of top dimension, and this can be evaluated on the fundamental cycle of X, and then we get some integer. And these are the Chern numbers, which are numerical invariants associated to the complex manifold. Yeah, I should remember that the product of cohomology classes, when we pass under the Poincaré isomorphism to homology, that the product of cohomology classes is just the intersection of homology classes. So this is something everybody can see. The homology classes are represented by subvarieties or subcycles of a certain dimension. You can intersect them more or less transversely, after moving them a little. And so these are actually intersection numbers. And so these are numerical invariants called Chern numbers. And so in particular, they are defined for projective algebraic manifolds, so smooth, embeddable in some projective space. projective algebraic manifold. This is the category which one is interested in algebraic geometry over the complex numbers. And in 1954, I wrote a paper in Annals of Mathematics where I said selection of problems, also which were given to me by other people, but I formulated in particular the problem 31 in this paper, asking which Chern numbers are topological invariants of the manifold. So under homeomorphisms of algebraic manifolds with each other, if such homeomorphism exists, the Chern numbers should be the same. So we asked this problem for the Chern numbers and for linear combinations of the Chern numbers. So what kind of topological manifold invariants you can get this way? And this problem was recently solved by Kochik in the proceedings of National Academy of Science this year. And he proved that among all linear combinations of Chern numbers, only the Euler number, which is the Chern number Cn, or multiples of it. So we can simply write only Cn topologically, because when we integrate it over the fundamental cycle, we can come back to topological invariant. If we integrate this over the fundamental cycle, we get the Euler number. This is Poincaré Hopf. So we get the topological invariant. Only Cn and multiples of Cn. So this problem was solved.
What about the signature?
Yeah, I said I have very little time here, and therefore I said isomorphism, homeomorphism. So I didn't say that the orientation should be preserved. And the thing that changes sign. Yeah. So I wanted to throw it out. So this is one of the versions of what Kochik proved. And he has to use difficult material about four-dimensional manifolds. Yeah. So that's quite amusing. And Kochik perhaps came to this problem because I considered again in some paper some old work of Borel and myself. Borel and myself studied homogeneous manifolds, in particular homogeneous manifolds projective algebraic, and gave methods to calculate the Chern classes of these manifolds and also the Chern numbers. And there was one example which I formulated as follows. This is a little bit modified by using remark of Calabi. Namely, so the old example of Borel and myself in a paper of 1958. Yeah, there we study the projective space, free space. Take its tangent bundle, and then you have in every point the tangent space, which is complex two-dimensional. Of this tangent space, in every point you can take the projective space. Sorry, that is two-dimensional. The tangent space is three-dimensional. So, okay, beautiful manifold, the projective bundle of the tangent bundle. Then the projective bundle of the dual tangent bundle, covariant tangent bundle. of the three-dimensional complex projective space. Then you can ask what is C1 to the fifth, evaluated always of the fundamental cycle. What is it? So we calculate, well, in this case it's 4,500, and in this case it's 4,860. So these are obviously topologically the same, taking the tangent bundle and the covariant tangent bundle and projectivizing, obviously topologically the same. Churn numbers are different. The algebraic geometers are very interested in the first Churn class because up to sign it is represented by the canonical divisors on the manifold. Divisors of a meromorphic differential form. So I guess Friedrich studied a lot these homogeneous manifolds as examples, at least he says so. And so this is a good old case to look at. Yeah, now it becomes a little bit more general, because we have Churn classes also for arbitrary complex vector bundles over some base space of a complex vector bundle E. So over each point of the base space you have a complex vector space. This is the bundle, locally a Cartesian product. Of course, you have such bundles everywhere. You can take the tangent bundle of a manifold, you can take the ith exterior power of this and tensor it with the p symmetric power of the tangent bundle, etc., etc. So there are lots of examples of vector bundles in differential geometry, and all of them have Churn classes. So by a similar definition, Churn class of complex vector bundle E of fiber dimension n. And if we think that the base space is X, so that this bundle is defined over X, then we have Churn classes Ci in H2I of X, always with integral coefficients. Yeah, that's the reason that all the Churn numbers are integers. You can always think of Churn classes also as differential forms, and the multiplication as multiplication of differential forms. And there are concrete differential forms describing them. And evaluating on the fundamental cycle means to integrate over the fundamental cycle if you work with differential forms. Yeah, but now we have for an arbitrary complex vector bundle E, we have these Churn classes, in particular Cn, the highest Churn classes, describes to you the locus of zeros, let's say, of a section of the vector bundle. Perhaps a section of the vector bundle is everywhere defined, and then the locus of zeros of such a section has something to do with the highest Churn class. Now, of course, there is a theory which allows you to calculate Churn classes of the tensor product or Churn classes. You apply a representation of the general linear group to a vector bundle to see what are the Churn classes there. This uses representation theory. This is all explained in my joint papers with Aman Morel. So now in particular the nth Churn class, as I said, corresponds to the locus of zeros of a section. therefore, I mean, this at least allows us to write down certain formulas how the Chern classes behave. So, if, for example, if you take the direct sum of two vector bundles, this one, let's say, of dimension fiber dimension n, and this of fiber dimension m. Then this has, if it takes a direct sum in every point, the direct sum of the fibers, then here you can worry about the Chern class C n plus m. So the locus of zeros of a section is the direct sum. Now you have a section in each sum end, then you have also a section in the direct sum which will vanish there where the section of E vanishes and the section of F vanishes. So the locus of zeros will be the intersection which corresponds to multiplication. So this will be the Chern class of the bundle E multiplied with the Chern class of the bundle F. Of course, we have to assume that both vector bundles are over the same base space. Yeah, so this is a product theorem. And now in the case of line bundles, suppose E and F are line bundles, so that means they have fiber dimension 1. Then you can take their tensor product. Then again you have fiber dimension 1. But there are many bundles with fiber dimension 1, and you can take over the same space, and you can take their tensor product. What happens now? We have only one Chern class, and the Chern class C1. What does happen with this one? Now the tensor product, yeah, fiber is always C, but if you take the tensor product, it means that the transition functions which describe the passing from one local description to another one, that they multiply. And yeah, so if I take a section in E, then we can multiply it with a section in F. Therefore, this vanishes if product is 0, even only one of the factors is 0. So therefore, we have the theorem that C1 of E tensor F is the sum C1 of E plus C1 of F. Yeah, but I mean, I try to motivate some very simple examples of the theory how to calculate the behavior of Chern classes under all kinds of operations on vector bundles. So in particular here for the tensor product of line bundles we have addition, and here for direct sum of any kind of bundles we have the product. This corresponds to union, addition of cycles, and this corresponds to intersection. The section of cycles if we go to some dual situation in homology. Yeah, now there is a difficult problem which I want to study as another example, namely let V be a vector bundle of fiber dimension 2. Takes a dual bundle. So these are in every fiber we take the dual vector space. Yeah, then I ask to you what is the mass symmetric power of V star. Now, you see, very elementary, assume that we have just one vector space. So the vector bundle corresponds only to one vector space. Then in this vector space we have coordinates. Let's call them xi and eta coordinates in V. Yeah, then these coordinates are a base for V star. Yeah, then what are, so in the case of a single vector space of dimension 2, what are the elements of the asymmetric power of V star? Yeah, these are the homogeneous polynomials. AK, AK, CK, eta to the R minus K. I mean, this is homogeneous polynomials in two variables of degree R. I mean, if eta is 1, if you are not working homogeneously, then these are just polynomials of degree up to R. So the dimension of this vector space is R plus 1. So if you do this now for a vector bundle, then this here, the fiber dimension, of SR V star is of dimension R plus 1. Yeah, now the question is how to calculate the Chern classes of the R symmetric power of V star. You must imagine that you have in every point of the base space a two-dimensional vector space, and you always, and you can consider the linear forms xi and eta, and then take the homogeneous polynomials in them. So this is another operation of tensor calculus to go from a two-dimensional bundle to this bundle SR of V star dimension R plus 1. Yeah, the highest Chern class is now CR plus 1, the highest Chern class. How to calculate it? By knowing the Chern classes of V star. How do you calculate this? If you know the first Chern classes, well, this is the question mark, and I give you the first Chern classes of the base, of course, of V star and C2 of V star. Now, so these are Chern classes, so in H2 of the base space, these are Chern of X, let's call it, of V star. Yeah, now by looking at this, following maybe is convincing, but I write these Chern classes as elementary symmetric functions of two variables x and y, where I consider x and y as formally of dimension 2. Yeah, and in the case that everything would be trivial or that V star could be split with the base xi and eta, then this corresponds to tensor product of line bundles, and this corresponds to direct sum. Therefore, you can imagine how the formula for the R plus first highest Chern class of the R's symmetric power of this two-dimensional bundle looks like. Oh, the other one, yeah. Well, there's still a lot of space here, but formula is the following. C R plus 1 or B star. So this is an example for all the calculations you can make by taking associated vector models. Like here's the symmetric power. Yeah, and I wrote the Chern classes as elementary symmetric functions of certain variables. And then this highest Chern class is, yeah, you can see there's a symmetric power. If you look at the expression in form of polynomials, is a direct sum of tensor products of line bundles. Yeah, in case that V star is maybe a direct sum of two line bundles, Chern class X and Y and so on. So you can have to take for each summand Ck tensor eta to the r minus k, you have to take here k times x plus r minus k times y, because I tried to explain that tensor products or line bundles correspond to sum. And then direct sum of all the summands in such a polynomial corresponds to product. So we take this from, what happened now, from k equals 0 to r. Yeah, like up there, there's also c to the k times eta to the r minus k. This is a symmetric polynomial in x and y, so you can write it as a polynomial in C1 and C2. So now you have an exercise of elementary algebra. Take this symmetric polynomial in x and y and write it in terms of the elementary symmetric functions C1 and C2 of x and y. You can forget now everything about characteristic classes. This is understandable in any case. This is symmetric in x and y. How to write it in terms of the elementary symmetric functions. And I give some example. If I take r equal to S3 of V star is, of course, for k equals 0, or for y, for k equals r, I get use of x, and for k equals 0, get use of y, so xy is in front. So we have x times, we have x times y times r square, yeah? C2 certainly occurs. Then I have taken care of the factors with k equals 0 and k equal r. But then we have 9 in front. And then you only have 2 factors left. And then the result is you get 2c2 plus c1 squared. Maybe it's wrong. That's the other way around. 2c1 squared plus c2. And now the next example is S5 of V star. Yeah, this is the case R equal 5. Yeah, no, R equal 4. Now I'm getting mixed up. Maybe I better look at my paper. Yeah, so you can, maybe it's now too elementary. Yeah, so the result is, this is correct.
C4. On the left you should write C4.
I don't know. What?
No,
S5
line,
of
C4 of S3.
Oh, sorry. Also there is some mistake. I want to, of course, to calculate here the fourth Chern class.
Yeah.
And here's the sixth Chern class, because I want to calculate the Chern class in the highest dimension. And then here I get 5 square C2 times 24 C1 to the 4 plus 58 C1 square C2 plus 9 C2 square. Okay, so I have also the next case, but that would be too much time to write it down. So I better leave it. Because I now want to study a classical problem as further example of characteristic classes. So I come to a completely first different looking topic, namely we consider the projective algebraic variety of all lines in the projective space of dimension n plus 1. So, if you take all lines, one-dimensional linear one-dimensional projective subspaces in the projective space of n plus dimension n plus 1. Now, for n equal 2, you have some sort of idea. You have all lines in 3 space, and if you look at it over R, over the reals, then you are really where we live. Space of all lines in the projective space of dimension n plus 1. And this projective algebraic variety of this kind we will call Fn, and the dimension of Fn, complex dimension of Fn is 2n. Yeah. Okay. And why is this so? Well, on this projective algebraic variety of lines in Pn plus C operates, of course, the unitary group, if we want to go to compact groups, make it easier, of n plus 2 variables. And this is a homogeneous space, this Fn. And if you have a line in this space, corresponds to a 2-dimensional subspace of the complex vector space of dimension n plus 2. A point corresponds to a 1-dimensional linear subspace, but a line to a 2-dimensional linear subspace in the vector space of dimension n plus 2. Here operates the unitary group, and if we have fixed a line suitably, then the isotopic group of such a line is U2, such a 2-dimensional vector space corresponding to a line in here. Yeah, the isotopic group is U2 cos UN. So you calculate the dimension n plus 2 squared minus 4 minus n squared. And then you should get 4n. Of course, twice. Yeah, one remembers that the dimension of the unitary group is a square number. So, okay. So, this is line geometry studied for n equal 2 by Felix Klein and Plücker in Bonn, 1868. Klein got his doctor's degree, or it was studied later for arbitrary n by Schubert, Hermann Schubert, 1885, Mathematische Annalen, Hermann Schubert, more precisely Hermann Caesar Hannibal Schubert. Yeah. And Schubert, 1885. So now we want to know something about the cohomology of Fn. And for this we take the tautological two-dimensional vector bundle over Fn. Yeah, because the points of Fn of the projective space are one-dimensional vector spaces, but the line corresponds to a two-dimensional vector space. And therefore, over every line, you have a two-dimensional vector space that has fiber, namely the vector space corresponding to this line. Yeah, this is projective geometry. So as we have a so-called tautological two-dimensional vector bundle V. A tautological two-dimensional vector bundle V, and its dual bundle V star. Yeah, so I take the first Schoen class of V star and the second Schoen class of V star. So this has complex dimension 2, and this has complex dimension, real dimension 2, this has real dimension 4. These are cohomology classes of Fn, and the question is, how are they represented? If we want to well, maybe I leave everything and take the new blackboard. So we have to repeat it again. We have this beautiful variety Fn of complex dimension 2n, consisting of all lines in the projective space of dimension n plus 1. Could not be more concrete. And over this we have the tautological two-dimensional vector bundle. We pass to its dual bundle. It has Schoen classes C1 and C2. And they should correspond to cycles in Fn of codimension 2 or 4 respectively. What are they? Now this cycle was studied by Hermann Schubert, namely C1. What is C1? Must have a variety of lines. Yeah. Now, if you take in Pn plus 1 a Pn, every line intersects Pn. But if you take a Pn minus 1, only certain lines intersect Pn minus 1. So you can take the variety of all lines in Pn plus 1, which intersect an arbitrarily chosen Pn minus 1. And this has codimension 1, complex dimension, and this corresponds to C1. So I've explained C1. I cannot write it down, everything. Yeah, so C2, it should have complex codimension 2. Yeah, but C2 is just represented by Fn minus 1. Because you can take in our vector space of dimension n plus 1, you can take a subspace of dimension n and take all lines in there. And this is the Fn minus 1 sitting in Fn. Codimension, complex codimension 2. And here for this we have the Schubert description. So now one takes the, again, like in the old Borel and myself example, but it was for a different space, you raise the first Schoen class C1, but in this case of V star, of the tautological V1. The first Schoen class of Fn would be n plus 2 times this C1. You take C1, the first Schur class of a topological bundle, and you raise it to the 2nth power and evaluate it on Fn. Yeah, what is the value? Yeah, you can either look into the paper of Schubert of 1885, or you look at a little bit more modern paper of Borel and myself 50 years ago, or a little more than 50 years ago, where all such characteristic numbers in principle are calculated, and therefore by one or the other way, but maybe we go back to Schubert. The formula is explicitly given there. This is the nth Catalan number, binomial coefficient 2n over n divided by n plus 1. The nth Catalan number, called, I will note it now, don't mix it up with Schur classes, capital C n. Yeah, the nth Catalan numbers, and we make a list of the Catalan numbers, C0, so it's 1. So these are the Catalan numbers, let's say CR, or Arque, or some other index K. For K equals 0, we have 1. For K equals 1, we have 1. For K equals 2, we have 2. K equals 3, we have 5, 14, 42, and so on. These are the Catalan numbers, which occur at hundreds of places in combinatorics. So now, yeah, it occurs here as this number. Now I have given to you the definition according to Schubert of C1. So this is the cycle consisting of subvariety of Fn, space of all lines. This is the subvariety of those lines which intersect an arbitrarily chosen fixed Pn minus 1. So now this number C1 to the n has the following geometric meaning. You want to take 2n-fold intersection. So how to do this? Yeah, you simply take in Pn plus 1 2n subvarieties Pn minus 1 over in relatively general position. And then you take all lines which intersect all of these 2n subvarieties. This is the number we are looking for. So, for example, in the three-dimensional space P3, n equal 2 in my notation, n equal 2, if you have P3, then the space of lines has dimension 4. So if you give 4 lines in P3, there should be 2 lines intersecting all these 4 lines. Now can we do this over the reals? Imagine 4 lines in P3 in almost general position. These 2 lines and 2 lines here. Yeah? How many lines are there which intersect all these 4 lines? Well, first of all, the connection of these points with the corresponding points there, and in addition, this line here, in the corner. Yeah, so now it is more difficult to imagine these 5 lines in P4. Yeah, so these are the meaning of Catalan numbers, and yeah, with this we now want to look at a problem, classical problem. Now, where in particular I can mention van der Waden, but I mean his exposition is different, but you can look at van der Waden, Mathematischer Journal, 1933. So, namely, we like to calculate the, as I did there already indicate, we take the what do I have? The 2n minus first symmetric power of the tautological vector bundle over Fn. So Fn is space of all lines with Vn plus 1. V tautological vector bundle, V star, it's dual tautological two-dimensional vector bundle. We can take its highest Chern class, because this vector bundle has dimension, as I explained, 2n. And we can take its highest Chern class. And this highest Chern class can be evaluated on Fn, because Fn has complex dimension 2n. So evaluate on Fn. Okay, then some number comes out. And of course, this number I practically gave you already. Namely, we have there the case n equal 2. First line on that blackboard, n equal 2. We have to evaluate this expression of Chern classes on the fundamental cycle. Now C2 always means that you go to an Fn of one index lower. C1 square means to take the Catalan number, which is 1 in this case, corresponding to the fact that two lines in the ordinary plane intersect in one point. But anyhow, this is 1. So we get there the value, C2 square, then we come to zero-dimensional Fn, this is 1. So there we get 9 times 3. So for n equal 2, this number is 27. And for n equal, this is not correct? What? First,
I'm reading the wrong line.
stimmt es. And the next n, for n equals 3, we take the second line. There we get 5 square. Then comes 2 times C1 to the 4, because this C2 always means going down to a lower Fn, and C1 to the 4 is the second Catalan number. The second Catalan number is 2. So this is 2 times 24 times 2 is 48. Then comes 58 times 1, first Catalan number. So 58. Is something wrong? No. It's plus 9. This would be 115, 5 times 23. So this is 5 to the cube times 23. So now you can continue calculating these Chern classes. So you see calculations with Chern classes are very down to the earth. And now, what is the meaning of these numbers? These numbers are the number of lines on a hypersurface of degree 2 and minus 1 in the projective space Pn plus 1. So in particular 27 is a number of lines on a hypersurface of this n equal 2 of degree 3 in P3. On a hypersurface or on a surface of degree 3 in P3 there are 27 lines, and there's an old model of Klepsch. Perhaps it's available here, I don't know. Klepsch and Klein, where the 27 lines can be seen over the reals. Yeah, why is this so? Yeah, I mean a hypersurface of degree 2n minus 1 is actually a symmetric element in the symmetric power of the vector space of dimension n plus 2, which is used to construct Pn plus 1. The vector space of dimension n plus 2 gives you Pn plus 1, taking all one-dimensional linear subspaces in Cn plus 2. And then symmetric power of degree 2n minus 1, this is a homogeneous polynomial over this vector space of degree 2n minus 1. Now, a line belongs to this, is totally lying in the space given by such a homogeneous polynomial. If the equation of this homogeneous polynomial is entirely zero on this line. But this means that this is, maybe if you take vector space Cn plus 2, actually I want to take here the dual space and then the symmetric power. Because I take this expression in terms of coordinates in Cn plus 2, the coordinates are linear forms over this vector space. So therefore you have this, and then you restrict this to V star, the tautological two-dimensional vector space bundle corresponding to a line. And then, the highest Chern class gives you the number of zeros for a section in this vector bundle. And the globally defined homogeneous polynomial is such a section, and the numbers of zeros of this section always given by the highest Chern class. Therefore, this is motivated. So the formula is for these number of lines is given by this, essentially given by this expression in the first line of the blackboard, and writing it in terms of the elementary symmetric functions of C1 and C2. So actually I was induced to consider these classical question of space of lines on hypersurface because I had discussions with Piet Moret of Max Planck Institute about such questions, because he has a paper with Grünberg on enumerative geometry, particular mentioning these numbers of lines. And so the question is the following. So here's another, do I have space? But maybe,
Can you raise something?
yeah, here is something.
What color is it?
No, just the lower half of this blackboard. Yeah, so, thank you. Yeah. So in this paper, there is an appendix by Don Zagier, because Zagier is unable to look at a sequence of numbers without studying their asymptotic behavior. Yeah. And so in the notation of this paper, Vn is the number of lines on hypersurface of degree 2n minus 3 in Pn. I prefer the notation of Pn1 plus Pn plus 1, because then the space of all lines Fn, the space of line geometry, has complex dimension 2n. That's easier to handle. But now Vn is essentially the sequence I studied in this lecture. So now Don wants, of course, the asymptotic behavior. And I did not check his result, but if you look at the appendix, you can see that this number Vn has the following asymptotic behavior. I don't know how does such things. For him it is probably simple. Square root of 27 over pi times 2n minus 3 to the power 2n minus 7 over 2 times, now asymptotic behavior more precise than just this, 1 minus 9 divided by 8n minus 111 divided by 640n square minus 9,999 divided by 25,600 dividing by n to the 3, and so on. So this is this interesting sequence of numbers for which Van der Wagen gave a formulation in terms of also symmetric functions in x and y somewhat differently, but essentially also the Catalan numbers is not much difference. So just to show you characteristic classes and applications in at least one concrete case, a question of number of lines on hypersurface of the degree given was the purpose of this lecture. So thank you.